Good afternoon, everyone. So let's continue our lecture. Let's look at the dimension for work. Please and please, this concept of dimension, it may look a little tricky or a kind of difficult, but it is not. Once you know the formula for a particular quantity, once you know a formula for a particular what quantity, you are surely going to know the dimension. And please don't forget, in my previous video, we only explained fundamental quantity and supplementary quantity. We didn't look at derived quantity. Yes. Any other quantity that are not, any other quantity that is not a fundamental quantity, it is not among the metal, and it is not a supplementary quantity, then it is automatically a derived quantity. For example, density, it's a derived quantity. Another one, work, is a derived quantity. So it is very easy to know anyone that is outside those um, um, fundamental quantities and the what and the supplementary quantities, they are derived quantities. Okay, let's continue with dimension of work. We know that work from formula, we know that work is force times distance. We use S as distance. So from law of motion, Newton's law of motion, F is the same thing as m mass times acceleration times S. You see, I'll be breaking the quantity down one by one. There's nothing I want to break this one down. There's a symbol, there's a dimension for this, that is capital M for mass. You see, this A, I still need to break it down. A is velocity over time. Now, this is distance, that is L. And it is remaining this one to be broken down. But I know that velocity over time, velocity is still distance over time. So that will now be distance over time. That will be distance over time squared. Because distance over time divided by time, that is going to be distance over time times 1 over time. That's distance over time squared. Now, what is distance? Distance is L. What is time? T, time squared. That's capital T squared. So let's combine all of them. That's going to be M, L. I can bring this T squared up. So everything will be up. That's going to be T raised to power minus 2 times what? L. Now, according to law of indices, this L raised to power 1, this L raised to power 1. So this can be M raised to power 1, L raised to power 1 times L raised to power 1, L raised to power 2, T raised to power what? Minus 2. That is how to compute dimension. You have to break the formula down into the fundamental quantities only. Then you can now substitute M, capital M for mass. Please, not small letter M for mass. Capital M for mass. Capital L for length. Capital T for time. If you use small letter, it is automatically what? Incorrect. Thank you. Take note of that. Now, we want to look at homogeneity of equation. Because in physics, we are going to be using a lot of equations. We are going to be using a lot of equations. So we need to know homogeneity of equation. This equation I want to use, is it dimensionally correct? Okay, if it is dimensionally correct, is it physically correct? You are going to know that today. So that when you write a formula, you want to use it, and you are not sure, there's a way you can test very fast and know whether whether the formula that you want to use is homogeneously compatible. So let's go. Now, for you to understand the concept of homogeneity, let's look at this. 5 mangoes plus 10 oranges. Can you give an answer to this? 5 mangoes plus 10 oranges. It doesn't make any sense. Mangoes are different from oranges. You can't add them together. I can't say this is 50 mangoes. I can't say, oh no, I have 10 oranges. No. What does it mean? It means that you can only have things that are the same, that are like that are alike. They are the same category. So you cannot add orange to mangoes, you cannot add mangoes to orange. Do you get the concept? So that's what we want to learn about homogeneity now. Let's go. Now, principle of homogeneity states that the dimension of all the terms on both sides of an equation must be the same. The comparison, addition, and subtraction of all physical quantities is possible only if they are of the same nature. They must be compatible. You go to get, you understand what is meant by that. Now, look at this equation now. And as I said earlier, that an equation might be dimensionally correct, but it is physically incorrect. Look at this equation. U squared is equal to U squared plus AS. This is dimensionally correct. But we all know that this formula is not used. This formula is dimensionally correct, but physically it is not correct. But look at this formula. This is the one that we normally use in equation of motion. V squared equal to U squared plus 2AS. This one is dimensionally correct and also physically correct. Why? Because it contains the normal, it is complete. These two supposed to be here for this one. Because the dimension, the two does not have the dimension. So the dimension will not detect that this is not physically correct. So from dimension, we cannot know whether an equation is physically correct or not. But we can know whether it is dimensionally correct or not. So let's look at the homogeneity of this equation. Now, let's do. Now, this is distance. Distance is mentioned, that is length, mentioned in capital L, that's the dimension. Velocity. Don't forget, velocity is distance over time. Okay? Distance over time times time plus half acceleration is, we have done that one before, distance over c squared. This is earlier. First of all, do velocity over time. So then it's going to be, velocity is distance over time. That's going to be distance over time over time. So multiply by c squared. I see that this t squared can take away this t squared here. And the t here can also take care of this t here. So now we are left with length here. What dimension for distance? Also length plus what dimension for distance here? Also length. You can see length is being added to length on the right hand side, and length is also being added. Length is also at the left hand side here. So we are adding length. This is dimensionally correct. You cannot add length and mass. If I have something like this now, L equals to mass plus L, it should be incorrect. It should be incorrect because you cannot add mass to length. They must be alike before you can add them. You get the concept? Let's give this a try. We have energy equal to half mv squared. We want to know whether this is dimensionally correct. Okay, let's go. We have energy. Energy, we can also use that as energy work for times distance. I come here, I want to check the dimension of this. Mass times velocity is what? Distance over time, but it is square. Square. So let's look at it. This is m times a times s. Do you remember that we have done something similar like this? Let's quickly go and check and pick whatever. We've done something like this. Here. We've done it under work. Can you see it? We've done it under work. Under work, we've done it. M1 L squared T minus 2. Let's go back. M1 L square T minus 2. This one gives us M1 L square T minus 2. Let's see whether we get the same thing. This must give us M1, M super 1. This distance squared give us L squared. You see, this one is going to give us over T squared. And when you take the T up, it's going to be minus 2. And see that what we have at the right hand side is the same thing as what we have at the what? Left hand side. So these are homogeneously compatible. That is, they are dimensionally correct. So let's go to limitation of experimental measurements. Now, when we carry out measurements, we do not get the exact value that we're supposed to get. Our value is always very close to the word value. When you are doing your simple pendulum experiment in school, you discover that the acceleration due to gravity that you got is not going to be exactly 9.8 something. It's not going to be exactly the standard value. Because why? There are several reasons for that. It might be because of the level of skill that you have in carrying out the experiment. It might be from limitation from the measuring instrument that you are using. It might even be from the way you even handle the measuring instrument. So that is why in any of our measurements, we normally take care of what we call uncertainty. What is uncertainty? Uncertainty is a quantity that measure how much the measured value deviates from the standard value. We want to know how far your values are from the standard values. That's what we call uncertainty. You cannot get an exact value in measurement. It is not possible. You cannot get the exact standard value, no matter how careful you are. So that is why you have uncertainty. Another word for uncertainty is called error. Now, how do you compute uncertainty? The uncertainty, if you want to find uncertainty from measuring instruments like your meter rule. Uncertainty from your meter rule now is going to be half of the least count. That is the least possible measurement your meter rule can measure. So let me give you an example of this. If on your meter rule, you can measure 5.1, you can measure 5.2, that means you can measure 0.1, 0.2 centimeter. The minimum you can measure is 0.1 centimeter. You see, that means the least count for meter rule is 0.1 centimeter. But that means from here, if you want to get the uncertainty, it's going to be half of this. How is it half of this? They assume that you have half of it to the right and half of it to the left. You commit an error to the right, you commit another error to the equal error to the what? To the left. So that is why they are dividing it by what? By 2. Take note. Because this is an examination question, and even several past questions miss the question. They say, what is the error in measuring with a meter rule? The least count on a meter rule is 0.1 centimeter, and which is equivalent to 1 millimeter, because they put all the answer in 1 millimeter. 1 millimeter. So the least error when you measure with a meter rule is half of 1 millimeter is what? 0.5 millimeter. So if you come across that question, the answer is what? 0.5 millimeter. That's the least measurement you can get from a meter rule. But if you are using a digital device, your uncertainty is the least count. If it is possible to get a device to measure length, and it is an electronic device, the error is going to be 0.1 centimeter or the least count, because we can't tell what the least count will be depending on how the device is designed. Good. So what do we call accuracy of measuring instrument? Accuracy of measuring instrument is the closeness of measure Accuracy of measuring instruments is the closeness of a measurement to the true value. So the higher the accuracy, the lower the what? Error. So all these have already been explained here. The least count, which is the precision, it tells you how precise your what? Your measuring instrument is, and also talking about accuracy. How accurate your readings are is depend on, like now, if you carry out an experiment to get acceleration to gravity and you are getting 9.8 something, you can see that even to get 9.89, look at that 9.89. If you approximate it to two significant figures, it's going to be 9.9. You and I know that that is not the exact value for what? Acceleration due to what? Gravity. So there's an error. So your accuracy, your reading is still a bit accurate because it's very close to the what? To the exact value. No matter what, your reading is going to be very close. It cannot be the exact value. So these are the precision of different measuring instruments, because if they ask you to calculate error, or uncertainty on any measuring instrument, these are what you need. Now, if you are dealing with micrometer, it is 0.001 centimeter or 0.001 meter. That's the smallest division. Don't forget, your uncertainty is going to be half of this if you are using a manual micrometer gauge. But if you are using a digital micrometer gauge, you are going to write this is going to be your error directly. Don't forget, uncertainty, if you are using measuring instrument that is not electronic, it's going to be half of the what? Reading. Because you are going to commit error to the left and also another error to the right. That's why you are dividing by 2. But if you are using a digital stuff, you are going to write the smallest division as your uncertainty. I hope that is clear. So you can go through this table. You can see this is the one that we use for metering. 0.1 centimeter, 0.1 centimeter. Don't forget, centimeter, you should be able to convert from centimeter to millimeter and vice versa at will. So now let's look at expressing measurement in standard form. Now, sometimes when you do your reading, you have to put your answer in standard form. Let's quickly do that. It's very, very easy. It's very, very easy. Now look at this. I will move a point from here. 1, 2, 3, 4, 5, 6, 7, 8. So 1.8. 1.8. Don't forget, the number must not be greater than 10. So 1.8 is not up to 10. Good. 1.8 times 10. Raised to how many times do we move it? 1, 2, 3, 4, 5, 6, 7, 8. 8 times. Good. Raised to power 8. You see, this 8 is positive because this number is a big number. But I've made it smaller by making it 1.8. So the power must be positive so that I can balance it off. Let's take a look at this. Sometimes we have a reading like this. 1675666. When you have a reading like this, you can put your reading to 2 significant figure or 3 significant figure. Because we assume that we are using your 4-figure table. Your 4-figure table is in 4 significant figure. So your answer should be to 3 significant figure. In fact, the best is for it to be to what? 2 significant figure. So, but I'm going to take this one to 3 significant figure. Let's do it. 1, 2, 3, 4, 5, 6. 1.6. But I'm not going to take the 1.6. The number here, this one becomes 8. 1.68 times 10 raised to power. How many times do we move it? 1, 2, 3, 4, 5, 6. Raised to power 6. You can see this is a very large number, but I've made this small by making it 1.68. So the power of the 10 is going to be positive. Let's do this one. Well, I want to put this one in standard form. 1, 2, 3, 4. So that's going to be 2.56 times 10 raised to power 4. Now look at it. 0.0000256 is a very, very small number. I've made it big. I've made it into 2.56. So I need to make this one negative so that I can scale it back to what the value that it is. Now, look at this. This one is very, very simple. I just move this one to this side. Then I get 1.0 times 10. I move it how many times? 1. Then is it going to be positive or negative? If you look at it very well, this is 10. And I've already made it 1.0, which is 1. It has to be positive so that I can balance it out. 1 times 10 will be 10. And that value will still be intact. So thank you very much for your time. So your next video will be ready very soon. Very, very soon. Thank you.